Hello and welcome to this session of ACS Science Talks, connecting the world through science. This is the virtual lecture series, Scientific Talks by specialists on specialized topics for a specialized audience. I'm Kunal Gupta and I'm pleased to be your host for today's broadcast of ACS Science Talks. I'm joined by my colleagues Dr. Ashish Mehto and Dr. Kaushik Natarajan, who will be moderating today's live Q&A. Our speaker for today, Dr. Dinesh Shetty. Dr. Shetty is an assistant professor of chemistry in the College of Arts and Science, Khalifa University since fall of 2019. He holds a PhD in chemistry from Seoul National University, South Korea. Following his PhD and before joining Khalifa University, Professor Shetty did postdoctoral stints at Winship Cancer Institute, Emory University, USA, at the Center for Self-Assembly and Complexity, Institute for Basic Science, Post-Tech, South Korea, and New York University, Abu Dhabi. He's a trained chemist with experience in multidisciplinary research areas including material science, porous materials, renewable energy, water purification, supramolecular chemistry, and biomedical science. He is the author of 55 peer-reviewed journal papers, more than 30 conference papers, 21 invited talks, and 6 patents with an H index of 27. Dr. Dinesh was selected as one of the innovators at Land of Dreamers Who Do at the UAE Pavilion of Dubai Expo 2020. In his career, he has earned several awards and accolades, including Khalifa University's Faculty Research Excellence Award, the Young Investigator Award from the Korean Society of Nuclear Medicine, and the Best Researcher Award from the Korean Center for Korean Cancer Research Foundation. A recipient of the U.S. National Academy of Sciences Arab American Frontier Seed Grant, he is a notable author profiled by Angewandte Chemistry International Edition. His global research talks and membership in the Royal Society of Chemistry under the Future Leaders in the Field category reflects his dynamic engagement. Beyond academia, he is a creative spirit, crafting poems, newspaper columns, and podcasts. His research centers on multifunctional material development for energy, water purification, and biomedical applications. So, thank you, Professor Shetty, for joining us today. The stage is all yours.
Thank you, Dr. Kunal. Thanks for the invitation. I hope everyone can hear me, right? Okay. Thank you. It's a pleasure. I think it's better to say hello instead of good morning, good afternoon, because they are from different parts of the world. So, hello, everyone. Today, I will be sharing a story from my group, because my group basically working on interdisciplinary science. But today's story is more about how can we tune the framework materials by varying the synthetic conditions. And then obviously, how can we use these materials for energy and environmental application? Basically, I'll be focusing more about water and CO2 reduction application. Okay, so because I'm talking about open framework materials, but because I'm including this application, it's about porous materials. When I say porous materials, as the name suggests, is porous, which means it has pores, right? So when you talk about pores, nature is everything, and we mostly copy, try to mimic nature. So look into the nature, the beautiful, the wings of fly, butterfly, or any other natural creature. So you could see a lot of pores within them. So when I say about porous materials, we're talking about, how we can observe this kind of porous structure within the nature. And then obviously we scientists try to mimic or copy or better version or alternative version of these kind of materials inside the lab, right? So when I say pores, say, for example, if you see the beautiful butterfly wing, there are pores. Obviously, we have observed that. But, and also if you see honeycomb, right? So there's different types of pores you can observe in the nature. So broadly, we classify them into disordered pores and ordered pores, which means when I say disordered, that's different size, pore sizes, and the arrangement itself is not in order. When we talk about polymer chemistry, what happens, if you have disordered pores, in general, we call them amorphous polymers. And when you have ordered pores, we call them framework materials. Both are having their own, benefits. But in my group, we are more interested in framework materials for a reason I will talk about. Okay, so when I talk about porous materials, I mean, the history goes back. And even today, people are using this porous carbon, right? Some people call it as activated carbon, but it's porous in nature. But the thing here is, this comes in this disordered pores category. It's amorphous in nature, and also important thing, it's full of carbon, but very limited functional tunability. You can't do too much functionalization to that. So that's why your applications are introducing different functionality to the amorphous structure of porous carbon is limited. But then goes realize you have another category of material, porous materials. They are crystalline in nature, but again, they have particular combinations here. So that's the reason it has less functional tunability. And also it contains metals. It has high weight density. In some applications, this is not a right thing to apply. So then in 1996, I think the major development in framework materials started by Professor Omar Yagi's group, they introduced something called metal organic framework. As the name suggests, metal organic frameworks. It has metal, it has organic component, and framework. It is a crystalline structure. They are highly crystalline, and they have a good functional tunability because you can vary metals, you can vary organic linkers to broad extent. So, but the issue here again, it depends on what application you're talking about. Because I'm referring to the application related to water purification. The issue here is about the high weight density because it has metals. Usually metals are heavy, but that's also beneficiary because of the metal presence of metal, you get better crystallinity as well. And another thing, because we're talking about coordination or dative bond here, and because of that, it's prone to hydrolysis, right? Because of that, most of the MOFs are water unstable. Of course, I mean, people should not complain about it because there are some MOFs that are quite stable in water, but in general, they are not so stable in water. But there comes then in 2005, again, same group, Professor Omar Yagi's group introduced organic material, fully organic. They are covalent organic frameworks. Again, as name suggests, covalent, which means the linkage chemistry we're talking about, covalent bonds. It's not the traditional covalent bond. Of course, we will talk about it. This is reversible covalent bond or dynamic covalent bond. They can undergo making and breaking process together if you control the kinetics. And also they have a completely organic course, right? So they are crystalline. I would say someone may argue about it, semi-crystalline in nature. And then they have high functional tunability here because you're talking about building blocks, you're talking about linkers, you can tune both of them, and you have a lot of tunability there. The good part of this is they have very low weight density because you're talking about fully organic system. So you can get the gravimetric advantage of this material for a lot of applications. And because it has covalent bond, definitely it has higher water stability compared to coordination bond or MOF structure, right? Not only that, especially let's focus our attention to covalent organic framework because that's what I will be talking about. So why covalent organic frameworks are really attractive? Because as I said, of course, they are stable, you can get the gravimetric advantage, but more than that, the good thing about covalent organic frameworks, you can control their pore size, right? Especially if you think about separation or selectivity, these kind of applications, this is really important one. You can not only controlling the pore size, and you can also even shape of the pores can be changed, can be tuned. Which means I'm talking about, for example, if we're talking about separation, I'm talking about the diffusion kinetics could be tuned because of this shape as well. Okay, and then another thing is you can do surface modification, and also you can do this the 1D channel formed because of this ordered structure. You can do the functionalization within the channel as well, so that you have a lot of things you can do, and you can introduce disability, you can introduce the defect. We will talk about it. You can do a lot of things with it. That's why it's a good resource to explore. And another thing is, for example, if whatever I'm saying in molecular level, if you cannot extend it into a macroscopic level, then you cannot explore or you cannot use this material for a real life application. But the good thing about TOF, you can take them into different macroscopic forms, especially very interesting ones like you can get them into foams, you can get them into membrane because membrane, that's where a lot of applications you can think of. You can make it as a nanosheets. You can take them into different forms. That's another benefit of this TOF, right? So now we talked about material because I'm talking about two important applications here. One of them is water purification because my first half of my talk will be about water purification. Again, I don't want to go into details because here a lot of people, I mean, everyone attending this meeting is well qualified and they know the value of water. The issue here is still a lot of people think we have a lot of water around us. But the matter of fact is, out of that, only 2.5% is usable water, right? Even with that, there are about 79% out of 2.5% is in ice caps or glaciers, and the remaining 20% is groundwater. That's what we are talking about. And unfortunately, because of many reasons, globalization, urbanization, pollution, a lot of things, because of that, groundwater level is going down drastically. Because of that, the question would come, what can we do? Of course, people talk about desalination. We can use maybe seawater. We can remove salt and get into it because especially where I'm sitting now in UAE or Middle East, we are heavily relying on desalination. But another thing you can think about it, how about reuse of water? Because there are places where water is once used, of course, we can purify that and reuse that. That's where the material scientists like me can jump in. So that's what we are doing in our lab as well. So this picture is not nice at all. Definitely not nice at all. This is the water crisis by 2040. I'm talking just 15 years down the line. This will be the situation. As you can see, the red color suggesting that extremely high, extremely over 80% high water stress, which means people really struggle. And I can see it even in my hometown, countryside of India. People are already struggling in summer to get the pure drinkable water, right? So that's why this is a serious issue, especially for many countries. This is a serious issue. Even if you see the other colors, basically within 15 years we will have water stress everywhere. It depends on what to what extent, but definitely we will have water stress. So water purification is very important area. But then how can we use this COF material for it? Then we have to go back to the literature. We have to understand the field where we are standing, right? So if you think about COF chemistry, I told you about framework structure. There are a couple of prerequisites to get the framework structure. In general, there are exceptions, okay? But in general, one is rigid monomers, because if you have a lot of conformational flexibility, it's very hard to get into a framework structure. It's hard to make them to sit at one place, and then this linkage comes to work, right? So generally, people are using rigid monomers, okay? And also planar structures are very good for this growth, right? So that's where you can end up getting the ordered structure, and mostly 2D structures people have been using, okay? There is a reason for that, obviously. But what we thought about going from 2D to 3D, obviously in my lab we are working on 2D as well, but I think for particularly for water purification, we are thinking of going from 2D to 3D. The reason is generally what happens when people are talking about 2D structure, that to order structure and 1D channels, they pictorially represent like this. For example, you have 2D, nice pores, right, ordered pores, and another layer coming up, and layers are stacking. So ideally, if layers are stacking such a way that if they open up this 1D channel nice, then it is very nice. Schematically, whatever we are seeing here, you can observe in real life. But honestly, 99% of the time, you will not get very well defined this 1D channel. Mostly, you will end up getting blocked channels, or you end up getting eclipsed channels. It's very difficult to, I think, those who are working in 2D membranes, especially COFs or any organic system, they may understand how difficult to, avoid the stacking problem or blocking this 1D channel problem. So basically, because of that, if you think about the water application, we're talking about the flux, right? Water flux, because water flux will be definitely affected by this phenomenon. And on the other hand, if you take 3D, because we're talking, when I say 3D, I'm talking about the 3D spatial connection of molecule itself, right? So we have the luxury of XYZ diffusion here, okay? But obviously, there is a section of people, they may argue about maybe 2D is better candidate. Yes, I agree, 2D is better candidate only if it goes with the ideal stacking pattern, okay? So, but generally, that is not the case. So that's why 3D could be an alternative, or it can have better benefits. That's what we were thinking. So that we had two basic questions, right? Yes, 3D COPs are maybe useful for this application, but getting 3D curves more difficult because getting 3D curves into a framework structure is very difficult compared to 2D curves. Okay? And the question again, yes, there are some reports you can get 3D curves, but can you get into the 3D curve membrane macrostructure, for example? That was the first question. Freestanding membrane I'm talking about. The next question is about can you tune when we talk about membrane? If you want to bring specificity or if you want to increase the efficiency, in some cases you need to do the modifications. People do synthetic modification, right? So then only you can bring the efficiency. But our question was, can we bring the same building block? Can we tune the physiochemical property of this membrane just by doing the synthetic tunability? That was the first question we asked, right? So my first postdoc in my group, Abdul, I think I'm sure he's in audience, a brilliant scientist. Okay, so he joined my group and we discussed about these two questions. Okay? Then he went back to lab and he started using the 3D tetraamine linker, building block, sorry, and then simple 2D linker. The chemistry is very simple. We are using a well-known dynamic covalent chemistry, imine condensation chemistry. And the one trick we played here is basically we did the interfacial synthesis, liquid-liquid interfacial synthesis, which means we have two different layers, immiscible layers. Obviously, the membrane forms in between these layers. Okay, but the change here is in one case we use ethyl acetate and water system. In other case, we use chloroform and water system. Same building blocks, please remember. Condition is same, room temperature. But to our surprise, what happened in case of ethyl acetate water system, we end up getting a membrane really hydrophobic in nature. You can see what is completely repelled. In both cases, we end up getting 3D curve membrane. That is first important step here. Okay, and then second case, what happened? The same building blocks, when we end up just changing the solvent from ethyl acetate to chloroform, we end up getting a kind of hydrophilic membrane. So that was a surprising thing for us because same building blocks, we didn't do anything. The method is different. Right? So then we try to understand why this is happening. On the other hand, if you do same synthesis in traditional solithermal synthesis, okay, then we end up getting again curve, okay, 3D curve, but this curve is having hydrophilic nature, not hydrophobic nature. Okay, so this is the crystallinity of that curve. It is a 3D curve with polymorphs, and then we did simulation to understand the structure and everything. But that is not important here. The important thing here is why this phenomena is happening, right? So to understand that, first thing, obviously, we did a basic characterization, molecular level characterization. If you look into the FTIR, in case of the membrane with hydrophobic nature, you have more carbonyl carbon. The carbonyl carbon group is more. Carbonyl carbon is coming from this aldehyde linker. And on the other hand, in case of less hydrophobic system, you have more imine bond, which means more conjugated system. What does it suggest you? It says that in one case, we have more defects compared to other case, which means what is happening here now, we are breaking to make it. Okay, we are introducing more defect just by changing the bifacial solvent system. Okay, then we did more detailed study to understand, how this works by increasing the amount of chloroform, slowly introducing into the system, and again we observe a similar observation. And we did the solid state NMR studies to understand. As you can see, in case of defect system, you have almost area under the curve 1:1, corresponding to the central carbon to carbonyl carbon. Okay, but on the other hand, less defect system, you have 1:0.1, which means it's again suggests that in one system we have more free exposed carbonyl group, which means defect. Right? So then why defects would give the hydrophobicity to the system? I think that is the basic question you may think. Obviously, I would love to explain it in detail, but in simple words, because these bromine CBr bonds are well known, bromine is well known to introduce some hydrophobicity to the system. And also what happens when you have a bromine and neighboring group, carbonyl group, you can have hydrogen bond as well. So it's a synergic effect, basically because of the defect area exposed to bromine as well as hydrogen bonding between them. It leads to the hydrophobic nature to the highly defect system. and on the other hand, hydrophilic nature to the other system. So then what we did, okay, is it true? Is bromine is really reason for this? Then what can we do? A simple control experiment. What we did, we took same tetramine and then we took a linker without bromine. Here also we end up getting the similar tendency, okay? When we observe the FPIR and all other characterization, we observe the defect fragmentation nature same. We observe the generality in fragmentation nature, okay? When we have ethyl acetate, we have more fragments or defects, or when we have chloroform, we have less. But the interesting thing here is when you have without bromine linker, even with the fragment system, the hydrophobicity is not to this extent. In this case, contact angle is about 142, but this is just 72. It's little higher than the other system where chloroform we are talking about, but still it is not there. So it proves or it justifies the bromine, presence of bromine is very important to introduce this physiochemical property. So what? We have a hydrophobic membrane now. The question we need to ask, what can we do with it, right? So because generally hydrophobic membranes are useful for oil water separation, and I am in UAE, so we are very much interested in this kind of application. And that's the reason what we did. We tried using this membrane as a freestanding membrane without any support. Okay? We are using this unisyringe filter. We placed the membrane directly into it, and we did the demulsification application. As you can see, in case of hydrophobic system, you end up getting a good flux, because that is very important criteria if you talk about separation. Very good flux for non-polar solvent. On the other hand, very poor flux for polar solvents like ethyl acetate and ethanol, understandable. In case of the less defect system, again you have a decent flux, but definitely this flux is less than the flux we are talking about other hydrophobic system. But on the other hand, it also has a decent flux for the polar solvent as well, which means this is not a great candidate. That's why we pursued with this hydrophobic membrane. And then what we did, demulsification application by varying the amount of water. But in this case, what happens when you have a mixture, water is completely repelled from the membrane. Okay. But we have to remove that water in between, otherwise it is blocking the surface of this membrane. Okay. That's the reason you end up getting a decreasing flux over the time. But if you continuously remove this water, then obviously flux is remaining. Okay, as you can see here with the different number of cycles. And this is the optical microscopic images. It clearly shows when you treat this with membrane, then you have no water droplets in the mixture. This is the story. This was the first story. We were very excited. We were able to publish it in 1990. Then again, I talked about freestanding membrane. I'm sure there are a lot of people in the audience maybe thinking about whether these membranes are mechanically stable, good enough, or what dimension we can get. All questions will be answered if you ask me. But yes, your doubts are right. So one of the problems when you talk about these COP membranes in general, not only this, but you cannot get into a very large dimension. Okay. And another thing, obviously, the mechanical stability of these membranes are not that great. So what we thought, okay, we have this property in this COF, 3D COFs. Can we use it with some other existing, very stable, mechanically stable and cheap membrane, okay, for real practical application? That's what we did. We synthesized this again. Of course, we did characterization, but the important part is here, okay? What we did now, we mix very small amount of this hydrophobic version of the COF with the cellulose acetate. It's a very cheap commercial membrane material. Okay, basically we want to use the 3D cup as a pillars, small nano pillars. Okay, so we mixed it, then using the phase inversion method, well-known method, we end up getting this membrane. Okay, but we use two conditions. One is we use NMP as a solvent. In other case, we use DMF as a solvent. What happened here when NMP as a solvent? The reason is our COF material is an insoluble material, but it has good dispersion with NMP. But it has a kind of relatively okay kind of dispersion with DMF. That you can see in membrane fabrication. When we did fabrication with NMP, you could be able to see a nice distribution of these microparticles of this COF within the membrane, right? But of course, up to what extent? When we went up to 0.8%, it's okay. And also, because of these pillars, they are introducing additional pores within this membrane. But when we go beyond 0.8%, what happened? the regio-specific aggregation started. Okay, that's what you can see. But on the other hand, when we use GMF, because the dispersibility is not that great for cough, we end up getting a kind of agglomeration. Still, we could able to get the membrane. But then also we did the cross-sectional analysis to understand, because what happens when we have this kind of hydrophobic pillars within, then when we do the phase inversion method, it is disturbing the flow of this solvent, right? And because of that, it is creating pores within this membrane. Okay, we have mesopores and different size pores within this membrane. Okay? So we end up getting a membrane, cellulose acetate membrane, having these cups. Okay. So then what we did all the characterization. Yes, we introduced this them as a pillar. So what? So we could able to improve the porosity of the cellulose acetate membrane. Okay. When you have a 0 means it's a pure cellulose, pristine cellulose acetate membrane. And when you go up to 0.8, the porosity is drastically increased in a well-dispersed system. Okay? CA1 means well-dispersed, CA2 means a kind of relatively less dispersed system. Okay? And if you think about the tensile strength, that's important for the membrane application. And in that tensile strength case also, when you have these pillars, you have a better tensile strength. Okay? In other cases, it's very difficult because different region, there is aggregation. So obviously, we can end up with kind of variable tensile strength. So then contact angle measurement, when we did this reverse case, when you see they are aggregated in regions, COF, then obviously COF is hydrophobic in nature, you end up getting a higher contact angle for that, the second membrane compared to the first membrane. Okay, and then we try to understand the surface charge of this and theta potential. When you see, when we introduce these COFs into the system, we increase the negative potential, which means negative charge of the surface. Okay? Because we have free OH COF as well. So we have a stable, mechanically stable membrane now. So what can we do? We tried using this for phenol removal from the polluted water. But this is a big thing, because usually phenol is coming to the water source through refineries and coking operations or coal processing. When I say all these things on a big scale, we are getting huge volume of water with phenol in it. Okay, but what is the issue with phenol? Obviously, phenol is carcinogenic. Carcinogenic means it can cause even cancer, along with other health related problems. Okay, so thing is heavy discharge to water source, so we need a solution, right? Of course, there are other people they are working, and because of this toxicity, Environmental Protection Agency, they allowed limit for this phenol within the drinking water is less than 1 ppb per billion. Okay? So there are removal techniques existing for a phenol removal. You are not the only one doing it, but there are techniques. The well-known techniques are distillation, adsorption, degradation, and membrane separation. Each technique has its own merit, pros and cons. Okay. In case of distillation, the issue is a good technique, but the issue is you need energy. You need to heat it up for the distillation. It's an energy-intensive system. Adsorption problem is you can do adsorption. The problem here is sometimes when you use the adsorbing material itself can cause a secondary pollution to the water. That is the headache. Degradation also same, because degraded product can be even more toxic than the original pollutant. Okay? So membrane separation is really a good one because you are not causing anything here. But the issue is getting the right membrane, getting a very good efficiency, getting good flex. These are all challenging things. So what we did in our case, we used this material, membrane, for the removal of phenol. But before doing that, we are using membrane. We have to check the flux. As you can see, the flux of our membrane with 0.8% of COF is much better than even pure cellulose acetate membrane. Okay? This is a porous membrane as well. So which means we increase the flux. Okay. Then we use this membrane for the phenol removal. As you can see, with a 0.8%, there is a saturation, even if you increase the amount of COF. With just 0.8% of COF as a pillar, you could able to get 82%. But the drastic difference here, cellulose acetate membrane, you are not getting much. Okay. And then what we did all this with the different pH condition, because we are talking about different water sources, there are different pH condition, different salinity. This is very important because usually we tried using this material for the water coming from oil refineries. because when you're digging oil, you end up getting this mixture of this water with the phenol. So that's what we did. It's performing really well. And then we did the regeneration because if you want to reuse, you have to use it. So we did the regeneration as well. And also after regeneration flux, whether it's maintaining same flux or not. So all in all, what is happening here, basically, this is not the separation direct, it's adsorption. The phenol, when it passes through the membrane, what it does, it interacts with the pillars within, and then they stuck there, adsorption basically, desorption, and then it allows water to go through. Okay, that's how we are removing phenol. Okay, this is the story we recently published. Then in our lab, we are trying different methods to remove the pollutant. One of the things we are targeting is emerging pollutants. They are very important ones now because emerging pollutants coming from pharmaceutical waste, plastic, the makeup product, and these are all very small amounts. They're usually in microgram to nanogram per liter concentration. That's why people call them as organic micropollutants as well. So the issue is people think if you have small concentration, easy to remove. That's other way around if you think about thermodynamics, right? So it's difficult to remove them with the classical water purification plants because they are not equipped for this. So that's what we need, alternative, a follow purification method. That's where maybe materials with good adsorption or good removal or good degradation is useful. So one of the methods we adopted is the bioremediation method, where we were trying enzyme to do the degradation of these emerging pollutants. Why enzymes? Because they are really good for, if you think about scalability, okay, and they have low input energy, obviously, and you can use it for a wide range of stuff because within enzymes you can get different types of enzymes. In our case, we are using horse red peroxidase, HRP, okay, and less consumption of reagents. You're not using too many chemicals here, and you can operate them at high and low concentration. It's not concentration dependent because enzymes are very specific. So now the thing is, then why can't we use enzyme directly? The issue with enzymes, they are biological molecules. They cannot resist the tough conditions, okay, whether it's a pH or a temperature. So if we can put them inside some porous support, okay, if the porous support can help them to go and sit, as well as they can help help to bring these small molecule emerging pollutants close to them, then obviously we can have a better catalytic reaction. That's why we used one of the coughs. In this case, we use different chemistry called Zinker reaction to get the stable cough and also introduce the cationic nature directly into the framework. And then we immobilized physically, this is option, immobilized enzyme to this framework structure, and we did all the characterization and everything. And the important thing here is we check the enzyme activity after immobilizing them on the substrate, and you can see the very good enzyme activity, retaining enzyme activity. And next important thing is the immobilized enzyme, if it comes out during the purification cycle, then it's not useful. So the leaching test is very important. As you can see, very minimum leaching, almost no leaching in the system, which means they are sitting happily inside the pores. And then the important thing is the temperature stability. So when we put these enzymes inside these pores, cough pores, the temperature stability drastically increased. That is significant. If you think about the scale up, you may think it goes from room temperature to 60, but this is significant because in some cases you need to increase the temperature. And in some conditions, automatically the heat of the column or heat of the membrane system is much higher than room temperature. That's why the stability is very important. Okay. And then we did the stability of this over the period of time. That is important. Then we tested a broad range of pollutants here. We took some representative pollutants from pharmaceuticals, for example, paracetamol. We took some pesticides. We took some pollutant from other origins. And the important thing here is when you have these enzymes within this cough, as you can see, almost 100% degradation. Please remember, we use very sensitive quantification system. Here we use LC mass and try to understand whether they are really degrading these pollutants. Okay, and also we check the percentage degradation for different solutions. Pretty much very good result for everything. So this is the story for that. Okay, so I'm just switching last 10 minutes of my talk to the other issue, we'll be talking about carbon dioxide. Most people are talking about now net zero by 2050, Paris Agreement. There are so many words and so many sentences or so many news you read or heard about because CO2 removal from environment is very, very important. But if you think about it, yes, CO2 is really not good for environment. It can have a greenhouse effect. But at the same time, CO2 is very abundant, cheap, so if we can use this CO2 into some value-added product, then definitely it's useful for circular economy as well. And also we are solving the problem of removing them from the environment. So there are many methods to convert CO2. Okay, thermal conversion, electrochemical conversion, photochemical conversion. But the one thing we are focusing the photochemical conversion. Of course, we are doing some electrochemical conversion as well. But for this talk, I'm focusing on photochemistry, right? So in this case, you need three components when you talk about photochemistry: light, charge, generation and separation, and the surface reaction has to happen. So you need a single system, semiconducting system, which can do everything together. Then this is an ideal scenario. So why cuffs are important? As I said, you have a tunability. You can introduce a catalytic center. You can tune the band gap to make them a favorable semiconducting material. And you have many other. You can introduce a continuous conjugation. You can do a lot of things with cuff. It's a good system. One such system is iso-indigo based system. Okay, so we use iso-indigo. It's a well-known acceptor. People used to use in solar cell application and all well-known acceptor. But we wanted to use this iso-indigo acceptor with the porphyrin as a donor to make a donor acceptor system. We end up getting this cuff. It took some time because of this flexible chain. Getting framework structure was a really nightmare. But we end up getting this, okay, with multiple conditions. And the good thing about this, it has really a narrow band, 0.7 electron volt. Okay. So then after that, because porphyrin is well known to hold metal center, so we did post synthetic metallation, and we introduced cobalt because cobalt is well known metal center used for photocatalysis, and we did further characterization. And then what did we do with this? We used this for a photocatalytic CO2 conversion in collaboration with Professor Mohammed Hamid group in Lebanon. And the important thing you have to focus here: when there is no light, no conversion. When you have light, there is conversion, right? But the thing here is just focus on this black graph. Then, as you can see, CO2 is converted into formate. Formate is industrially very relevant chemical. It's a very useful one. And in presence of light, it can go up to about 11 micromolar concentration conversion, CO2 to that. Then we did number of cycles. We have to see whether this catalyst can be used. Then we try to understand the mechanism, how it is happening, who is doing what. So in this case, what is happening is the metal center is the cobalt, obviously. The light is absorbed by the conjugated donor acceptor system. And that's how we end up. But when we talk about the CO2 conversion, generally we have to confirm whether the CO2 converted format is coming from CO2 or somewhere else. So that generally people do this isotope labeling method. And we did that too to confirm this is the format converted from the CO2 source. And then the last story from for this talk from my group, I talked about the cough. I talked about for CO2 coughs, for 3D coughs, 2D coughs. But now I'm talking about something called MOFs, but very specific MOFs, the conjugated MOFs. There are different reports using the symmetrical molecules, okay, to make conjugated MOF system. But we are the one we introduced this the kind of no symmetry here. We have a carbonyl and OH hydroxy group, and also we used mechanochemistry instead of using classical solid thermal chemistry. This is much more easier, scalable method. Okay? And this is our report. Recently, we reported this method, and now we are scaling it up, and we are using it for many applications. We did this characterization. For example, in this case, we used copper and nickel as metal centers, and the TP as the monomer unit. And it's a very easy mixing. And then thermal treatment leads to the formation of conjugated system. Then we thought of using them as a salt-free system, which means, for example, we use copper salt and TP. Instead of that, how about dipping this copper foil, for example, inside the TP solution? Can it form a cough? So we could easily see beautifully formed, not COF, MOF, beautifully formed MOF on the surface of copper foil, and we characterize them, and also it is showing the semiconducting nature, and we end up getting the semiconducting conjugated MOF. And what did we do with this? We use this conjugated system to do the CO2 conversion, in this case CO2 to carbon monoxide. It's another very important industrially valued gas, right? So in this case, we end up getting a decent conversion of CO2 selectively, 100% selectively, because we checked whether it is giving any other gas products. It's not giving, and also we could reproduce that result for at least 4 cycles. Okay, so this is the story so far what we have. Last 2 minutes, I will tell how, I think there are some students here, how the simple observations sometimes inside the lab can lead to a very nice scientific work. Okay, if you remember this system you are familiar with, we used the 3D linker and 3D building block and 2D linker interfacial synthesis. But in this case, what we did, we control the reaction kinetics by doing open and closed system. Before we use this interfacial synthesis in open system completely. In this case, what we did in a closed system for 6 days, then we opened little to make it partially open. Okay. The interesting thing what happened here, in first 6 days, we end up getting amorphous polymeric film. But after, once we do partial open system, slowly the hydrogen bonded frameworks made of oligomeric COFs, and they come and self-assembled on this, and due to the strong hydrogen bonding, they are staying on the surface of this COF film. So the beauty of this work is you can easily convert the chemical gradient into a different form of the framework formation here. In one case, amorphous film, then you have a hydrogen bonding network sticking to that. And then we did all study to understand what sort of interaction it has, why it is forming, and then we try to, I'm rushing just because of time, why it is happening, try to understand the mechanism by microscopic analysis, right? Here, as you can see, over the time, in first 6 days, what is happening, as I said, film is forming, COF film, amorphous. And then after that, slowly, things started to form, and we end up getting this one-dimensional crystal, nicely self-assembling on the surface of this COF film. But if you think about it, you're talking about same building block. Usually when we talk about hydrogen bonded network, right, HOF films, okay, hydrogen bonded organic frameworks, it's very difficult to get into a film form, membrane form. So in this case, what happened, we are lucky, first it forms amorphous film. Over that, the hydrogen bonded organic framework formed. The overall package leads to a mechanical stability. We end up getting a very nice freestanding membrane. What is happening? To our understanding, what is happening? In the beginning, there is a free flow because there is nothing in between these biphasic systems. So they can meet each other. They can start react fast. Kinetic is fast. Usually when you need a framework structure, you have to reduce the kinetics. So then the COP film is formed. COP, COP, film is formed. Once COP film is formed, you have a barrier between these biphasics. Then the diffusion of this building block is controlled, right? Once it is going, it is reaching, less number of building blocks reaching upper layer, and same time you opened it, okay? When we partially open, what happened? The upper layer has organic layer, right? They started evaporating, and the concentration of other monomer increased drastically compared to here, right? Okay, that leads to a formation of this 1D crystals, and they slowly stack, come together, have a very strong hydrogen bonding, and then they form that film. Okay, what is the use of this? Because it's a hydrogen bonded organic framework. Generally, it is used for proton conduction, right? So we tested this proton conductivity. The interesting observation you have to do here is if you have just COP, okay, that's why tunability comes into play. If you have just COP, look at the conductivity, and at least 4-fold increase in proton conductivity when we have a half over COP. Okay, so we end up getting this conductivity. And another thing, the activation energy required for this is much less compared to the commercial Nephron membrane. For example, it's 0.21 electron volt, I guess. So in our case, it's a 0.14 electron. So just to tell you the story, uh, it was a kind of observation. Then we went little deeper into it, and we are lucky we end up getting into a nice story, and we published very recently. So just last message is, I mean, our work is highlighted in Expo, as you mentioned, and I strongly believe, I think this is the message I want to give everybody. I think the most valuable gift we can give to our kids is pure water or pure air. I think for next generation, if you sit and think seriously, this is the key. Okay, we can buy apartments, we can buy a lot of other things. I think the important thing here is giving a pure air and pure water. This is invaluable in future days. Okay, so last one, just to thank people who are responsible. I'm here to talk, but people who are responsible are people in my lab. The most of the works I covered here done by Abdul and Nada and other people helped along. And also we have a lot of other collaborators, and I'm thankful to them. And I hope I didn't go too fast. I tried to cover whatever story I wanted to tell, and thank you for listening. I would be happy to answer any question.